Hello everyone. In this video, we will work through one of the sample problems from the note package for part 6 on gravitation. The following problem has been slightly varied from the one shown in the note package to highlight a key aspect of the solution process. The problem is as follows. Suppose the Earth pulls down on an apple. We want to determine the following. A, what is the acceleration felt by the apple? And B, what is the acceleration felt by the Earth? So for this problem, we will be given the following values. The mass of the apple, denoted as ma, will be 0.816 kilograms. The mass of the Earth, denoted as me, is 5.98 times 10 to the 24 kilograms. The radius of the Earth, denoted by re, is 6.38 times 10 to the 6 meters. And the gravitational constant, denoted by capital G, is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Regarding the distance between the apple and the Earth, because the radius of the Earth is so much larger than that of the apple, we'll simply let RE be the distance from the center of mass of the apple to the center of mass of the Earth. Neglecting the radius of the apple will have essentially no impact on the final answers. As with all force-related problems, we'll begin by drawing separate free body diagrams for each object. Even though the system being examined may seem trivial, there is always merit in drawing such diagrams to identify all the relevant forces and the directions in which they act. Doing this exercise for simple systems is also good practice for examining more complicated configurations. So for the apple, we'll draw a small circle and indicate its mass with ma. We'll include a coordinate axis in which the y-axis is labeled with an r to represent the radial direction pointing to the center of the Earth. It is along this axis that the gravitational forces act. We then indicate all the forces acting on the apple, which is just the force of gravity due to the Earth, denoted as Fg. Because there are no other forces acting on the apple, Fg will cause the apple to accelerate to the Earth. We'll then indicate the apple's acceleration off to the side as A subscript capital A. For the Earth, we'll draw a larger circle and indicate its mass with me. We again include a coordinate axis and indicate all the forces acting on the Earth, which, in this case, is the force of gravity due to the apple. Note that the Fg for the apple will be the same as the Fg for the Earth. This is what connects the two free body diagrams. And finally, because no other forces are acting on the Earth will accelerate to the apple, which we'll label off to the side as A subscript capital E. We can now determine the acceleration of the apple to the Earth. We'll start by using Newton's second law to determine the net force acting on the apple. Looking at the free body diagram, the only direction in which forces are acting is in the radial direction. This results in a net force which is expressed as the apple's mass times its acceleration. Now the only force acting in the radial direction is the force of gravity, which thus equals the net force. The force of gravity on the left-hand side is given by Newton's law of gravitation, while the net force on the right-hand side is given by Newton's second law of motion. At this point, we have everything we need to solve for the apple's acceleration. We could simply substitute in the numbers and solve for A. But this is not recommended, and we'll see why in a moment. Instead, we will solve the equation for A in variable form first, and then substitute in the numbers as the final step. Now, because the masses of the apple appear in the numerator on both sides of the equation, we can cancel them. Bringing A to the left-hand side, we then obtain the final equation in variable form. We then substitute in the numbers and obtain the final numerical answer, which, surprise, surprise, is the value for the acceleration of gravity. So going back to the original relationship, if we simply substituted in the numbers at this point and then solve for A numerically, there is the potential for round-off error as we manipulate the numbers on either side of the equal sign. However, what is worse is that we would miss out on a key observation, which is that the acceleration of the apple to the Earth is in no way influenced by the mass of the apple. We can clearly see this in the equation for A because the mass of the apple is absent, which we would miss if we just started plugging in the numbers. This is one of the key aspects of physics through which scientists gain insight in how physical quantities are related to each other. Intuition would suggest that the apple's mass would affect its acceleration, but the equation for A that we derived clearly shows and thus proves that it doesn't. In fact, ignoring air friction, as we did, we would get the exact same equation for any object falling to the Earth regardless of its mass. So in the absence of air friction, all objects fall to the Earth at the same rate, whether it's an apple, a feather, or a bowling ball. Finally, we'll determine the acceleration of the Earth to the apple. As before, we use Newton's second law to determine the net force acting on the Earth. And as before, we equate the force of gravity to the net force, which once again leads us to the force of gravity on the left-hand side given by Newton's law of gravitation, and the net force on the right-hand side given by Newton's second law of motion. Solving the equation in variable form now shows us that the acceleration of the Earth to the apple depends only on the mass of the apple, not the Earth. Plugging in the numbers, we find, as we would expect, the acceleration to be virtually non-existent. So the ability of the apple to accelerate the Earth is, for the lack of a better word, futile. This concludes the presentation of the solution to the sample problem. Thank you for your time, and take care.